And now we are going to finish this chapter with functions as arguments of other functions. We have already seen an example of that in the previous section, okay, when we saw lambda functions. Well, this is very common in numerical analysis, okay, like function optimization, root finding, dynamical systems, because sometimes we need to use a function as an argument of other functions, okay, probably from other built-in libraries, but it may be one of our own built-in libraries or imported libraries, okay, but it could be something from our own, from our own work. It could be. So in this case, we're going to find numerically the roots of the transcendental equation e elevated to x equal to x plus 2. Okay, and this is equivalent to defining the function f x equal to e to the x minus 2, and then finding its roots. Okay, so in this case we are going to use the SciPy library. So if you don't have the SciPy library imported, but I think that you have the SciPy library imported, installed, if you use Anaconda, you just have to install it, okay? And you can find documentation about this, the function that we're going to use here in this link. Now we are we are going to import this function, which is inside the module optimize, which is in the SciPy library. Okay, so first of all, what I'm going to do is to define a function here, a lambda function in this case, although it could be a simple function, with the function definition, a standard function definition. And we are going to define this function here, okay, e to the x minus 2. Since instead of writing e to the x, I'm writing the exponential of x, okay, which is a function which is defined in NumPy, and it works very well this way. It's not very nice to write e elevated to x in Python. It's much better to use the exponential function, okay? So now what we're going to do is call this root scalar function from SciPy.optimize, and we're going to call it with these arguments, okay? The first argument is going to be the function. I'm using just the definition of this link, okay? So if you look for this link, you're going to see that, this function is going to have many optional arguments, and we are going to use a few of them, very few, to make it simple. In this case, we're going to use this is always going to be the first element, okay? It's the function that we want to find the roots from, and we are going to use this optional argument, which is going to be a bracket, okay, which is the interval where we are going to look for these roots. And the method that we are going to use is the bisect method, okay, which is the bisection method. Let's see how this works. When we call this function, okay, this is the result of this function. The result of this function is going to be an object of a certain class, and if you print this object, this is what you obtained. Okay, notice that here I have lost the return of this function. It's just lost in the air, okay, it's lost in the rain, like teardrops in the rain. So here what we have printed is that it has converged already, okay? The flag converge means that it went very well. The number of function calls are 42, and the number of iterations in order to find this root are 40, okay? And the value of the root is 1.1461, blah, 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 blah. Okay, so let's see. Let's see, with Matplotlib, we are going to print these two functions, okay, the exponential of x and x plus 2, and we are going to see if this is more or less correct, okay? So we can see, in fact, I'm using here the easyplot function that I defined before, okay? So here I have that the link space x is going to be the link space from 0 to 2 with 1000 points in between, and this includes 0 and 2. And this is the bracket that we were using. Okay, this is the bracket that we were using to call this function root scalar. And the result is this for the exponential and this for the linear function. So we see that these two lines, this cross each other in this point of x. Okay, and well, it must be this value over here. So if we do this, the mathematical function, but using the usual definition of functions this way, okay, notice that we have done exactly the same. Okay, this is np.x minus x minus 2. This is exactly the same, but with a function definition, a standard function definition, and we call the function with this, we are going to call the function with this function definition. Now in this case I'm going to define a new bracket, okay, and I'm going to use another method now. Notice that I mean this, as you can see, well, you know that the exponential goes from 0 when x goes to minus infinity, goes to 0, and it goes to plus infinity very quick when x goes to infinity. So the infinity of the exponential is much larger than the infinity of this linear function, of any linear function. So but the linear function, we know that it goes to infinity when x goes to infinity to plus infinity, and it goes to minus infinity when x goes to minus infinity. So what we have here is the crossing point when the exponential wins the linear function, okay. And here but I mean there must be some other point where the exponential is below, because, well, I mean I'm sorry, in this range the exponential is above the linear function, okay. In this range the exponential is below the linear function, but there must be another range, okay, where the exponential is again above the linear function, because the exponential goes to 0 while the linear function goes to minus infinity. So in this case we are going to look for this root in this interval, in the -3, 0. And the method that we're going to use is a Brent method with a quadratic approximation. The Brent method, I think it was based on, I don't remember, Regula Falsi maybe, I don't know, I don't remember. The point is that in this case we also get this function is going to converge to the desired value, okay, which is the root in this interval. We are, in this case, only 9 calls to the function were necessary and only 8 iterations were necessary, and the root is this one over here. So if we plot these two functions in the interval -3, 0, this is what we're going to obtain. Okay, notice this is the part where the exponential is below the linear function, and here we have that the exponential is above the linear function. Okay, this is the other crossing point, and this is the first crossing point and the second crossing point, and that's it. I mean, these are two examples where we can use functions in order functions as arguments of other functions in order to obtain some property of the function that we're studying. Okay, so that's it. You will have to do some exercises of functions during the class, and that's the end of the course. I will try to, but I'm not sure. Okay, maybe I will do some videos regarding the classes, but I'm not sure about that. And that's it. Okay, see you in the class. Bye.